Now let's look at the initial value problem for a second order linear differential equation. Well, note that the initial value problem for a first order is different. So for a first order differential equation, if we have, well, suppose nonlinear, the initial value problem specifies the initial condition as the value of the unknown function at some point. So the initial value problem for a second order differential equation, it specifies both the unknown function and also its derivative. So that's the kind of the extra step for second order differential equation. So here is an example. So this is a well-posed initial value problem for a second order linear differential equation. Well, strictly speaking, it doesn't have to be linear. So the important thing is that when we work with second order differential equations, then the initial value problem includes the value of the unknown function at the given point and the value of its first derivative at the given point. Well, and here is the theorem about existence and uniqueness of solutions. So if we have a linear second order differential equation, and suppose that its coefficients p, q, and g are functions of t continuous on some interval, right? So then this theorem tells us that the initial value problem has a unique solution on the same interval. Well, now if you recall the previous lecture, then in the previous lecture we had exactly the same theorem for first order differential equation, and for first order we were able to prove this theorem explicitly by constructing a solution of the initial value problem. However, for first order, for second order, it is kind of harder, so we're not going to prove it. Well, I'll write will not prove. The reason is because second order differential equations, even linear ones, cannot be solved explicitly. So to prove this theorem, you really need to apply some careful estimates on the growth rate and so on. So it's not that easy. Okay, so I'm going to skip on the proof of this theorem for second order differential equations, but I'm going to give you some intuition behind it, and some intuition behind, well, why the initial value problem for second order differential equations has to specify the value of the derivative and not just the value of the unknown function. Well, but the main most important point probably that is clear immediately is that in order to specify the solution of a second order differential equation, we need to define the values of two parameters, right? So the value of the unknown function and the value of its first derivative, and therefore the general solution of a second order differential equation is going to have two constants, two parameters, not one parameter like for first order, but two parameters. And well, you can guess that generally speaking, if you have a differential equation of order k, then its general solution is going to have k constants, k parameters. Well, now here is the main reason why this theorem holds is because you can convert a one second order differential equation to a system of first order differential equations by introducing a new variable that represents the derivative of the unknown function, right? Well, but then the initial condition then translates into the initial condition for the two unknown functions. Well, and then the uniqueness and existence theorem for second order differential equations, it is just follows from uniqueness and existence theorem for systems of two first order differential equations. Well, and here is the general Picard-Lindelöf theorem for a second order not necessarily linear differential equation. Well, and then if you review the proof of the Picard-Lindelöf theorem very carefully, you will see that it works without any change for systems of differential equation rather than for individual differential equations. So, which means that the theorem that you see here, not only we can prove it, but we already proved it in the last tutorial. Okay, and now I suggest that you stop the lecture and